We're now at the end of the unit, and it's time to start bringing together everything that we've learned from this entire unit. So, the eventual goal here is to learn about solving these optimization problems. And in these optimization problems, we're going to have to optimize some certain situation under constraints. And so, what we're going to be doing is we're going to be translating the constraints into inequalities. We'll then graph those inequalities. We're going to look at where they overlap at, which is what we learned previously. We're going to find the corner points of where those lines intersect, which is systems of equations. And then we're going to try to figure out, of all the points that work, including these corner points here, which one optimizes our situation. So in order to get to that point, we're going to have to look at translating these situations into inequalities and equations. Now, the first thing that we're going to be working on translating is going to be constraints. Constraints are going to be these requirements that we have to live under. And so we're going to have to turn these into inequalities. So let's look at some strategies. So this particular constraint that we're looking at says write an inequality represent the following constraint. Mowing a large yard, which we're going to signify as X as the number of large yards, uses half a gallon of gasoline. While mowing a small yard, which we're going to signify Y to be the number of small yards, uses a tenth of a gallon of gasoline. We have 9 gallons of gasoline available. And so this constraint is going to be to say, basically, how many large yards and how many small yards can we mow before we're out of gasoline? And so we need to look at translating this to say, for every X that we do, for every large yard, we use a half a gallon of gasoline. So if we mowed 4 large yards, that would be 4 halves, or 2 gallons of gasoline. And so we could represent that with multiplication. We could say, if I multiply 0.5 times X, that right there is going to be the amount of gas used on large yards. But then if we looked at our small yards, we use a tenth of a gallon, or 0.1 for each of those. So we could similarly say 0.1y is going to be the amount of gas used on small yards. And if I want to know how much gas did I use total, well, I'm going to add those together. Now, we only have 9 gallons total. So if I had said, don't write this down, if I said equals 9, then this would be an equation in which we use every last drop of gasoline. But we want to create an inequality to say, well, we don't have to use every drop of gasoline. It would be okay if we use less than that. So to create an inequality here, we want to say the total amount of gasoline needs to be either less than or else equal to 9. Now, we don't want greater than 9 because if we need more than 9 gallons of gasoline, we don't have enough. We're not going to be able to finish that lawn. There's going to be a couple strips of tall grass left. We don't want that. So this is how we're going to create an inequality. We're going to look at how do I represent the situation that's there. And then we're going to take a moment to look at the inequality direction and say which makes sense. When doing so, you want to take a moment to decide, do I want to be less than this final value or more than it? But the other important thing to consider based on the different situation, they're all going to be different, is do I want to include that value or not? So in this case, I would say go ahead and include it, because if we used exactly 9, we would be fine. Obviously, this is not an exact science. There might be a tiny little bit of gas left, or there might be a little bit of grass left, one or the other. But in this case here, I would say include it. But there's going to be times where we might not want to include it, like saying, we want to have at least 1, and so we need to have more than 0. So at least 1 could be greater or equal to 1, greater than 0. So we're going to look at it that way. Now, the other type of thing that we're going to need to translate are going to be the objective functions. The objective function is going to be this function that we're trying to maximize or minimize. That we're going to try to make as big as possible or else as small as possible. And this function is going to include both of our variables, and then this is going to be a third value that's going to be written in terms of these variables. So in this example, we have a fence company that sells wooden and metal fences. We're going to let X represent the number of wooden fences they sell and Y to represent the number of metal fences. They make a profit of $370 for each wooden fence and $220 for each metal fence, and we're supposed to write an objective function that can be used to determine how much or how many of each to make in order to maximize our profit. So in this case, we generally call our objective function z equals, but what this z is representing in this case is going to be total profit. That's what we're really trying to find, is the total profit we're going to make off of our business here. And if X is the number of wooden fences, and we're making $370 for each of those, then we're going to have 370X. This is going to be our profit from wooden fences. And then if we look over at the metal fences, we'd want to add in the 220 times Y of those. That's going to be our profit for the metal fences. If we add those together, that's our total profit. And this is going to be what we call the objective function. What we're going to look at later then is we're going to say, hey, if I can narrow down the possible combinations to maybe 5, that it's one of these 5, then I could plug them all in to see what the total profit is for these 5 combinations, and then look at those 5 combinations and decide which one would maximize the profit? Which one gives me the most profit out of these 5 different combinations? Because we might have some different constraints that maybe, yeah, you make more money off of wooden fences, but maybe they take longer. And so maybe we got to look at that and say, all right, well, we need to stay within these constraints of time and things like that. So that's what we're going to look at a little bit later on, is to say, all right, which combination maximize our profit if wooden takes us less time or more time, metal takes us more, and then maybe there's something else as far as supply and demand that we can only get so many of one or the other. So that's what we're going to be looking at a little bit later on, but as we're translating, we just want to kind of break these apart and kind of take them simple at a time and say, all right, what is it I'm looking for? If I'm looking for total profit, then I need to find the profit from the wooden and the profit from the metal, and that's the kind of thing we want to look at.